Hello. I would like to have some audio check and video check if it's possible. I would assume it works. I set up a few things, but you never know. Okay, I assume that does work. Alina, could you confirm it, please?
Yeah.
Okay, so we are ready to start.
Yeah.
Good. So I should proceed with my slides. So morning, everyone. I'm going to have a lecture, giving me a few minutes to find technology. And good. Again, I lost my slides, sorry. Just a moment. I'm having troubles to share my screen. I'm sorry about that. I'll reconnect. Hello again. Okay. Host disabled screen sharing. Excuse me, Alina, I need your help to allow me to screen share.
You need to share a screen.
Yeah, it just said that I wasn't allowed to do that. Host disabled screen sharing. Oh, yeah. Now it's back.
It's okay now?
Yeah. Okay. And I think we're live finally. Do you see my screen?
Yeah.
Good. Whew. Sorry for this delay. And welcome to lecture of this morning in Lviv Data Science Summer School. Thanks, Alina, for help. And for the next couple of hours, I'll try to drive all of this. So today's lecture will be about graph neural networks and a gentle, in a way I can do it gently, introduction to all this space. I'm trying to make this more informative to understand the building blocks, context, but I will be diving a little bit less about specific optimization techniques, more about building blocks and how we can apply those to some real problems. So it's more motivation with few leads, how to dive deeper into this area. So a bit about myself, because I was told there won't be any space for this. I finished Kyiv Polytechnic University, and then I had a few years of my own run company when I got interested in semantic web. That pitched me my PhD scholarship. I spent a great couple of years, 4 years, at the University of Southampton. And since I went back in industry, for the last more than 5 years, I'm in Facebook, and I've been working again with in academia. I've been working with graphs and dynamic processes on graphs, and now back in industry, I again working with graphs. I started with community sharing in advertising, studying lots of content consumption. Then I've been mostly focused over the last 3 years on integrity problems, dealing with fake accounts, if the easiest way to describe this. And lately, I'm joined Facebook Applied Research, which is also focused on community integrity problems, but we're bringing more cutting-edge technologies to this. And this talk will be basically what my team does right now. We're bringing graph neural networks to applications at Facebook. We're trying to scale it up, develop new techniques. So about the talk today and what's on it, I'll give some introduction about graph and networks, why we see them everywhere, and how basically every complex problem can be reduced to a graph. Well, not every, but many of those. Then I'll introduce GNNs. It's graph neural networks. It's one of the approaches. It's not the only, but one of the approaches which is developing quite a lot over a recent couple of years. And what are the building blocks? I'll try to basically explain how does it work and how we bringing deep neural nets to train on graphs, and basically which problems we are solving with that. We'll have a questions and break, and then we'll continue with another little bit shorter session, depending on how much in depth we'll go into demo, as giving some bit of broader context to GNNs, and I'll have very quick run on the demo, how to basically build your own one using one of the most popular libraries. And then we have another questions. And as always, you can follow up later in Slack channel or offline. So please ask questions during the lecture. I'll try to keep the Slido open. Otherwise, we will have dedicated break towards the sound have a bad quality and it's soft. Yeah, so here's the first question. I'll try to correct it. Just give me probably a second. I was trying to use my headphones specifically to correct for anything. And please don't hesitate to give comments also on Slido or later on Slack on the questions. Meanwhile, I have another fighting session with Zoom. Okay. As you can see, I'm not a frequent user of Zoom, and it confuses me. Okay. I'm trying to increase the volume of my sound. Okay, this is one place. Audio settings. Okay. I'm sorry about that. That's odd. Okay. I'll try to then. Okay, I'll try to rely on automated sound correction. If technologies fail us, there'll be another follow-up for everyone to improve. Okay, so I'll proceed with what we have. Sorry if it will be quiet for some. Okay, great. Thanks for confirmations. Yes, so I'm glad to see that we already have questions live and I have some live feedback. So please continue this. I will be coming back and forth, and maybe Alina will be help me to mark those that are answered. I will have Python demo at the very end. It'll be a very brief one just to show you how to start things. And there will be a link for a couple of hands-on tutorials, which are really deep and you can spend more than a day on that. We're lucky that this is fairly actively developing area and we can find lots of cutting edge demos. So also there is a Slack channel. We'll follow on the Slack channel after the lecture with any questions or details. Now back to the lecture. So finally to the content. The first part is basically what are the graphs and why do we need to study them and why we need to learn them. So we actually see graphs everywhere, and it's not just maps, but this is the first example that you could think of. It's a London Tube map. And when you see the graph, you may necessarily see topology, but always when we work with them, we abstract them. And the first step we would think is basically about abstract graphs. We always convert even our geographically accurate graphs into something like abstract plan. And all graphs we're going to be dealing with are abstract plans of actually of the processes we see in the world. And this one, it basically somewhat simplifies the geographic ones, but most importantly, it does lots of extra information, magnifies bits which are important for us. And you would be thinking about all graphs we're dealing with some abstractions. So this is an example of abstraction, but we will be abstracting way more. Here is like ultimate graph of how the whole internet looks. And this is the Internet Map project, also sponsored by Google, where they're trying to see how different websites basically interact with each other. And all this linking map converted in a huge humongous graph. So all graphs basically penetrate us everywhere, and we can mine some information out of these graphs. An example of mining information of graph is like the first one you would always give as PageRank. And the first version of Google, which were basically based on PageRank and trying to figure importance of pages by how much information flow into this. And I don't want to dive into this. There are so many actually interesting examples how to mine this. Just giving a few more examples. The first one, which really matters to me in my work, is a social graph. And social graphs are basically everywhere right now and has been very active research study area for the last 10, 15 years. And when you dive into the details of social graph studies, I'll give you an example of one of the earliest ones. We see that basically even structure of an organization is reflected in the communications. And here is one of the first analyses of properties of graphs, and this is HP Lab email communication. And when we see all the structure between people hierarchically in bold lines, all the communications between those people are pretty much reflected those. So the analogy here is that we can recover from interactions between people and graphs also inherit structures in our societies. In this case, for example, organizational structure. This work was very inspirational for me, and I've been reading a lot of academic work before I actually went into my studies. And I've been very lucky to find Lada joining Facebook before even I joined. And she's continued working to study actually societies and network properties and publishing papers from inside of Facebook. All these networks, they have lots of interesting properties we're not going to touch today, but just to remind you, there are these small world properties. Basically, even people from very distant part of network have very small number of hops in between of them. It's basically communication always have limited number of hops in graphs which are arranged naturally. And maybe you've seen this meme of we are 6 steps separate from anyone in the world, which is not exactly true, but it describes these ideas. It has other properties. I don't want to dive much into that. Here's an example of individual in a graph. If we'll go into social graph, and here I've picked up my LinkedIn example, is where all my communities around me, and you can see here probably my uni, my PhD years, my work in one company, and a few other of my social circles that I join. So all this information allows me to kind of make conclusions probably about central nodes, me, about my interests, who am I connected to, and maybe also what I would be interested in doing recommendations. I'm just checking the questions. Okay. So what's really striking about graphs and important for us, everyone, as graphs also help us to study epidemics. And this is why we're all sitting home. We're not right now in Lviv. I would love to be in Lviv, frankly. We model society and dynamic processes in society as graphs. So if I showed you previously a social networks as static ones, our dynamic interactions in the world are also a graph. We're exposed to a certain number of individuals, they're exposed to another set of individuals, and we can mimic, model basically our society on a dynamic graph, and we can model how disease, epidemics, viruses spread in societies. And these models have been around a while. They started in physics with statistical mechanics, and now becoming more and more accurate as we better capture the properties of societies. And probably you saw many of those models. They are right now becoming more important and more refined to project. For me, this work was very inspirational because when I went to do my studies in my PhD, I actually looked into information sharing. And specifically, I looked into how conflicting opinions are shared. I ended up looking into this direction. And information sharing and disease sharing actually at the basis very similar models. Again, our space in which we basically do all these operations are graphs. And here you can see Twitter where conflicting opinions, how they're cascading across political debates in America. It was back in 2010. So what I did is very simply, as illustration, I was trying to figure how we can improve accuracy of opinions in society by exploiting or relying on social properties of behavior. And specifically in this illustration, if we see a graph, and this is very illustrative as a grid, just to visualize it, each one is an agent which basically consumes and shares information. And I've been working on how these agents independently need to study how to basically put trust or fuse information from this neighborhood, such that on overall society will become a collaborative filter, and they'll start filtering more accurate predominant opinions. It was very interesting work, and this work was a bit much earlier than GNNs. It was back in 2008, 2007 when I started it, where GNNs were just starting, but it deployed very similar aspects that I'll show you later. Each individual's and this network node, as our modeling element, can study something myopic in its neighborhood, as we basically consume information Twitter only reading our followers. So graph applications are vast. We have graphs everywhere, and this basically why? Because we can decompose lots of complex problems as interaction between parts, and interaction between parts results in a graph. I don't need to reiterate on internet. Games as alpha game or chess game also can be decomposed into a graph where you will have basically board position and legal moves out of this board position for this piece. You probably, when you did algorithms in computer science, you would see that many algorithms decompose into graphs in a similar manner. I spoke a lot about social relations and how message exchange build those. Interesting that molecules and drug discovery is also can be simplified to graph problems, because each molecule is a combination of atoms with different bonds, which is pretty much a graph. And there's lots of work to understand how each molecule, specifically proteins, how they fold, how we can predict properties of different drug discovery. This is very cutting edge, which drives GNN work. 3D Scan, which is computer vision, counterintuitively is also a graph where we basically model different parts of objects that we track into a graph. For example, like our limb is pretty much a graph because we can discover and connect together all the nodes. And I don't need to talk about transportation. So before I dive into this, I check the questions. can someone without knowledge of neural networks work with GNN? Also, does this course demo use Python? I answered yes, it does demo Python. Whether we can use GNN without knowledge of neural networks? Yes, there are basically deep graph learning applications which do not need to rely on neural networks, and those are more probabilistic. I'm not touching them in this course. So in some sense, we can reduce every problem to graph and use slightly different mechanisms. GNNs is one of those. I'll highlight a couple of alternatives, but I'm not going to dive into this lecture in those. Will the video be available on YouTube later for reference? I do believe for next 2 weeks it will be available. And can BGNN apply to scheduling transfer systems, prevent bus bunching? Yes, and this is basically one of the applications I saw around, and in the review papers I will attach later, you probably will find specifically references that you may find of interest. Now, what is a graph? And now we're going a little bit more into scientific part. We abstract. So we realize that some things are around there and we need to work on abstracting those. So we can reduce those to nodes, and they're also called vertices, points. There are lots of alternatives, but I'll try to stick to nodes as the main one, and edges. They're also called links. Occasionally I'll be using links because it's quite often used in domain, relations as well, and other literature also calls this arcs or arcs, but point is the same. So it's basically a set of two and combination of two sets, and we have edge is basically as a pair of vertices. And in this case, we may have edges which are directed and undirected. And undirected edges, I will be simply modeling through this lecture as basically a set of two pairs, just to simplify and not to think about that. So when we see undirected edges, we would be assuming that there is also a pair which is permutated oppositely. And there are also a couple of properties on edges which are crucial in our discussions. We can have loops, self loops, when nodes point to itself. It's not less often, but it happens. We can have also loops in terms of, on the first undirected example, where information may flow in a circle, which creates lots of problems to some of the very simplistic algorithms, which really just trying to work as a tree, trying to constrain information sharing in the graph. We'll be discussing how this is done. And yeah, this is the basics that we just need to know. It's fairly simple. Now, when we will be discussing graphs, and you saw graph properties like transfer graph we just mentioned, usually will carry also some semantic knowledge about the hub, about, for example, if it's a transfer station and how many people are passing through the transfer station, was basically its operational hours, and also some data associated with relations between or links between these nodes. And we will be encoding those additionally for this set of features, for this set of nodes and edges as associated feature vectors. And here I demonstrate for node a feature vector, which is basically as you know, as an embedding, as basically some vector of float numbers, which allows me to put into some representation space. We can assume that it's coming from underlying algorithm. Quite often, if it's a textual document, this is going to be some representation of text using existing text representation models, and links might be how authors refer to each other, and the problem for us would be trying to predict new authorships or paper authorships. So these things will carry some information, and we will be thinking about this as properties of a node, properties of edges. So now graphs not necessarily consist of single type of edge or a single type of node. And I will be introducing another part of our consideration how we describe graphs is basically types of nodes and types of edges. And we also assume they are just mapping for each node. We know its type. For each edge, we know its type. Here's an example to demonstrate. It's also a part of GNNs, heterogeneous GNNs, and these graphs are called heterogeneous graphs. So we have basically different types mixed together. Here, as I previously described, we can have different nodes, and this is author, belongs to some institute, who has written a paper in certain field and certain venue. And this is quite a well-known data set in which graph studies are being conducted, is basically citation networks of academia. In these graphs, we can try to understand where authors work, predict fields for papers which haven't been classified yet, trying to discover hidden links between authors that working in the same domain but probably hasn't collaborated between yet, and so on. So the last bit which we need to understand about graph notation is the neighborhood. And this is when I spoke briefly before about social networks, is about how actually each node or agent, if we're thinking about social network, sees its surrounding. And this is basically a neighborhood of a node is a list of nodes which are one hop vicinity. Hop is basically a distance from this node to another node. And in this case, this is undirected graph, and for node number 1, 2, 3, and 4 other neighbors. For node number 2, only 1 and 3 their neighbors. In directed graphs, we often talk about neighborhoods of in and out neighborhoods. And in our GNNs, we'll be assuming we're talking about in neighborhoods all the time. But the most important to understand this concept is that each node is myopic and only can see and consume information from its neighbors. It's basic assumptions that we make. So well beyond the scope of this lecture, the graph properties and study of networks is a fairly vast field of mathematics with applications across the computer science, in particular for me, or physics. And we can talk about lots of other properties. I will leave this for later, but I just highlight that you always need to think how sparse or dense graph, how basically many links. If graph is completely connected, is a complete graph, and basically all nodes are connected. But it might be sparse. It might be sparse, it's disconnected, that pieces of graphs are actually floating separate. If graph is connected, we can actually measure how diameter of a graph, how basically many hops we need to pass from one edge to another and to another on average. We may find components of graph which are connected and only think about those as separate components. And I already spoke about some connectivity properties. I'll leave this for later. It's for you to discover. It's not really necessary, but it's really understanding the graphs that you model helps you to give insight which modeling techniques are best to use and how to better optimize it. It's basically when you map your problem to a graph, you make lots of design choices. And it's good to understand these design choices when you make. So there are lots of graph properties and problems that are beyond the scope of today. This is kind of graph algorithms you probably saw all over the place as traversal of a graph, finding paths, finding flows, is how to split and find these communities, partition graphs, and how basically to describe which nodes are the most influential in graph, how to color code graph, it's very popular in computer science and mathematics, and how to basically try to compare graphs. All these problems beyond the scope, we just probably need to know about them for problem modeling. So now finally, we're diving into machine learning tasks. And what actually tasks we do with graphs? I'll split them into unsupervised, which basically we don't have any labels, and we're trying to learn some inherent information embedded in the graph. And the first that comes to mind is link prediction. We have a graph, and this is, for example, a social network of people, and we would like to predict who between those people we probably should recommend to each other. Similarly, it can be a product network, and this is consumers consuming products, and it's a bipartite graph where we can recommend new videos or new goods to buy. Another part is, which is very important for us, is representation learning. And this is very common representation learning also you saw from text, images, and it can be completely unsupervised, where we basically taking inherent information embedded in text, and then we can map any, by training on large corpus, any other text, how it relates to domain of previously static ones. And this one, we basically can learn how to, given initial features of node, edges, and property of a graph, how to represent these nodes, links, or edges, or the whole graphs. And that would allow us probably to do graph comparison or later use this representation of nodes and links in later tasks, same as we do with text today. Supervised and as supervised task, the most nice one to demonstrate is classification of graphs or predicting properties of graphs. And the one which really sweet is drug discovery. We can look in a molecule as a graph, trying to predict side effects of this molecule without doing clinical studies and trying to prune very early bad components. This is very active research area. I'm not vouching details on that. Then semi-supervised is probably what we're going to be looking most at when we have a graph and we know something about it. We know some properties of nodes, and we know that, for example, certain nodes are certain types, and we want to predict others. In my work, we know, for example, that certain pieces, certain accounts are abusive, and we would like to find other abusive accounts in the whole network. And then generative learning for graphs, which I actually won't be touching much today, but you probably seen in machine learning is basically quite active development of work, generating images, generating text. Same applies to graph, and we can actually generate graphs. And again, this is generating molecules or generating better social structures that mimic what we would like to model. That can be useful not just for modeling, but also for anomaly detection, for predicting actually how the existing graph will develop, which might be very important for us to have any prediction task. Okay, can we solve these problems without graphs? And this is very nice problem. So graphs are there, problem is a graph, but do we really need graphs to solve it? And frankly, no. We can actually, well, yes, we can solve it without graphs. We don't need graphs. And I have these examples daily in my work, and this from our Facebook work in integrity. They have been exposed mostly last couple of years and working right now. So link prediction or classification between two accounts, between two pieces of content, not necessarily has to be modeled as a graph. Yes, graph brings lots of interesting information, but also that probably will require a little bit of more work. That will require for us to develop these technologies we currently develop, and they were not available, or the work had to be done quicker. And so we can do it much quicker and simpler. We shouldn't be shy of actually doing that, because it's always 90% of performance is a very simple method, and maybe they're not needed to do complex. But then at the end of the day, with more elaborate methodologies, we show exactly contributions about these baselines. So link classification can be, or prediction can be simply seen as we split the whole graph into pairs and engineer features for each node, or comparison features as basically links between those, and using any binary classifier to predict, are these two nodes connected, or is link between these two nodes a certain property. For example, recommendation engine can be done in very naively in this way, and actually will work, despite there are better methodologies. So we currently use these technologies, and we right now building substitutions for this. But since there was a lot of feature engineering invested into these baselines, it's fairly hard to beat. Let's not be mistaken. It's always a problem of feature engineering against better modeling, and we need to trade those together. Second one, which actually even more highlights of importance of feature engineering, and you can see in depth in this link, it's was Abuse at Scale conference from the last year, presenting our deck entity classifier, which is used for abusive accounts detection in Facebook. It's a huge machine which consumes large portion of actually our infrastructure for feature extraction and prediction. And actually it's responsible for deleting billions of accounts. The whole idea how it works, we can see that actually it's graph, and it's graph of accounts connected to pages, connected to groups, connected to other accounts, connected to posts, to everything that actually can indicate an abuse. You can spam in a message, you can spam in a group, you can spam in a page, you can create pages. There are different ways of actually of abusive behavior, and they need to be captured all. And this is basically a graph. So for each of this account we're trying to classify, we extract this neighborhood of a graph and aggregate the features. And here's the problem. Basically, this local graph, ego graph, because it's centered around the central node, needs to be converted into feature vector. And for this, we aggregate all these features numerically, and we apply lots of different sampling and aggregation techniques, like taking for all accounts that are also friends with this account, there are various variants of certain properties, averages, P25s, or categorical, trying to measure entropy, how basically typical this behavior of this account in the network. This all results in 20,000 features. This is one big vector, and it becomes flat. So basically, we convert this ego graph into flat structure. Inherently, we'll lose some information, but also we can scale this up very quickly. And that was been done, and this work evolves fairly quickly. I actually already what I'm describing you is an old version, despite this what been presented in last year, and we're already using GNNs in part of this infrastructure, not yet fully. They're already showing improvements. They better learn these features by themselves instead of doing this all feature engineering, how to aggregate these features, and I'll dive into that deeper. And last bit, example of my work we kind of see as multimodal entity classification. We're trying to predict properties of a post. And this post is basically not necessarily a single entity. It can contain video, it can contain photo, it has text, it has author, it has comments. And this is all actually starts to become a graph. A graph actually where else this video has been used or has been this photo reshared and actually it's existing post. So we can compress those together into set and use deep set models, or we can model it in a graph. And we can see already that graph, these links bring some information incremental to previous methodologies. Okay, so this has been description of my work, and I see questions coming, and I'll dive into that because it'll be break for me. What programming languages do you use in your daily work? Do you use SQL to manage data? So in our daily work, we use things that work. And this is nice bit, and this is kind of also you need to learn lots of things. When I moved through industry, I changed programming languages. Mostly, I'll be frank, I stayed with Python. But in my previous team, where I've been doing more applied fake account detection, I even used Haskell for deploying some of our work. Still, our modeling techniques and our machine learning pipelines were in Python. Let's not be mistaken. Behind Python, there is a huge infrastructure of very low-level, highly optimized code, and Python is just a high-level glue. So PyTorch, for example, let's say a library is not, it allows you to program in Python, but behind the scenes does very optimized coding. For data management, we use lots of SQL, and we had the largest Hive deployment in Facebook. Right now, it's converted to Spark Hive QL. We build Presto, is new in-memory databases, and this is lots of data processing in SQL, but equally, you can write some smaller pipelines in other beans that are necessary. Mostly right now, I rely on SQL because of just sheer efficiency, how to manage very large scale of data sets. When data sets are small, yeah, this is not really a problem you can do in Python. You can do pandas, and this is it. Next question is, in what field is it inevitable to use graphs? Why? What are the predictions for the future regarding companies' usage of GNNs? So I will try to delay these questions for a moment, and I'll answer this at the end of this section. Okay, so because this is coming with this slide. So why actually, if we can do this without GNNs, and I showed you just these models, actually they've been running without GNNs for years, and I believe there are lots of industries like that. Why do we need GNNs? If we look at machine learning pipeline, actually, it's all over the same. It's basically we have raw data, very simplistic if you squint a little bit, which is we do feature engineering to make it structured. So basically with raw data, we do some problem modeling and extracting features what we believe will be important for us to train a model. And quite often we do this feature engineering, some basic models like logistic regression requires us to do base transformation, require us to do combinations of features. We need to really just think what will be the most predictive for a task. Then we apply our model, which actually then leads to task. For example, classification, predictions, regressions. So these bits can be improved. And this is kind of all neural network studies and deep learning, which brought these improvements to us. That it really tries to take away the work that how do we basically do feature engineering simply from manual work to directly ingesting raw data like images and image recognition, text, usually the most prominent examples. And actually, instead of doing feature engineering, trying to find edges on the image, color blocks, or doing word separation, it tries to learn these all semantics on the fly and doing basically this feature extraction by itself. So learning in graphs and using GNNs allows us basically to get a tooling that will extract from raw data the most important features for our task. It's a holy grail for deep learning models. So basically, if I showed you previously, we had this model with 20,000 plus features. It's not like those features are gone. They're still in graph, but right now this whole extraction, the number of those features exploded actually because we had lots of different ways how we aggregate them. But right now we have a neural network which actually learns how to aggregate features from neighborhood of an actor, of an account, in the best way to predict abusiveness. So, and the most important, why actually, this whole graph, it has inductive bias, relational inductive bias. It's actually a property of our domain, which we discard when we do feature engineering. We basically really can lose lots of information. So the structure that we have in a graph, especially in social network, if we're trying to do predictions inside of social network, is really crucial for us to reason about neighborhood. If we'll reduce everything to features only around each account, around a single node, we'll never be able really to predict more distant relations and do friendship recommendations which are more distant than single hop away. So it's crucial to improve tasks dependent on relation, structure, context, which are often lost in feature engineering. Okay, so I'll answer the questions right now, those. And again, in what fields is inevitable to use graphs? What are your predictions for the future regarding companies' using of GNNs? So first, I'll start with the future usage of GNNs. GNNs is very dynamic work stream, and despite first work started 10 years ago, pioneering works, only recently, last couple of years, 3-4 years, it became really appealing. And only kind of through the last year, we're really establishing a very good baselines, even how to evaluate and compare the works. So this is a very active area. And the answer is very simple, is they have to prove themselves. So they're proving themselves right now in my team. We're basically trying to prove that GNNs work on very applied applications in integrity space. And my prediction, they will work. But will they stay exactly as I described them in today's lecture? Probably yes as building blocks, but not as models. I do believe that models will evolve. We're actually working by ourselves, trying to figure out what are the best models and probably what is the best development of these models. But the whole way to think about a graph in this way that I'm going to be describing probably will stay. Which feels inevitable to use graphs is a little bit harder to answer. Because of my exposure back from academic past, I actually see graphs everywhere because how complex problems can be reduced to interaction of the parts. Now, there not necessarily have to be graphs, as we basically learned a lot from applied examples. Why? Because graphs are very complex to work with. This was the real reason why we haven't had actually GNNs 10, 15 years ago, or we're only recently coming to basically understanding how to use it. Similar with like image processing and text processing, we're building better building blocks which allow us to abstract some of these complexities. So I do believe it will be coming way more to use everywhere you see a relation. So instead of actually right now trying to relation between entities convert into feature, we can just preserve it and trying to train simultaneously together a heterogeneous graph, for example, as a prediction between different goods and consumption, between different goods, because then we will learn how actually these goods related to each other and how consumers related to each other, and how if we especially have some extra information which allows us to link consumers. These all things we previously squeezed into features. So it's early to answer, but I'm not gonna tell you that's gonna take the world, as any technology is gonna prove themselves. And this is very exciting to work in a place where you're basically trying to prove those things. Next question, do you deal a lot with NLP? So personally, I am not touching NLP, but in my team, people do. And they work with predicting properties of, I know people actually that work with NLP to predict properties of misinformation, which is very important and hard problem. And they're trying to do their best. And actually, GNNs is showing very promising results in that space. Please watch the space where publications will be coming up. How it actually works, that we not directly mixing NLP and graphs, we create representation of text and then using them relation between texts and other entities in order to do our reasoning and classification. But I also saw the work not internally. We have a latte team which works in NLP specifically, another applied research team. But I saw in the academia work where we model sentences as trees or graphs. And also I saw sentence generation in NLP relying on GNNs. I cannot tell you much more. I'm not a domain expert in this area. Okay, next question. What do you think about MATLAB or Octave? Do you use it? I used MATLAB and Octave back in academia, and up to a level that I did lots of modeling of graphs, and especially MATLAB and Octave, they allow working with matrices quite easily. And despite I'm not going to be showing the matrix notion of algorithms today in this lecture, just for simplicity, they all exist. And they fairly easily could be transferred to MATLAB and Octave. My take on MATLAB and Octave, we don't use it right now a lot because it's a little bit harder to scale it beyond a very small group of 1-2 person. And our industrial, yes, frankly, because the way how basically designed to work as a research code, the syntax of the language, a little bit of lack of abstraction to do sharing code. But this is my private opinion from experience. So that's why we basically rely on more generic languages that will allow us to later productionize and build its infrastructure. So frankly, I haven't been using MATLAB and Octal for going to be, I don't know, 7 years. Next question. What are the biggest challenges in your work? Do you feel frustrated, excited? Well, yes, and quite often both at the same time. Challenges in my work, the more I'm moving into applied research, and I've been doing quite open work in a previous team where we're trying to find actually what is the problem, how to deal with the problem, and how to tackle the problem. Quite exciting always to come to the new problems and trying to understand how to improve them. So my previous problem where I was dealing with certain type of fake accounts, one of the type of reporting that you probably will find deep in reporting flow inside of Facebook reporting accounts when you're telling us it's a bad account. We were trying to automatically discover and mitigate this problem. It was very open domain. We even didn't know how to properly measure it. And that was quite active research of us measuring it, trying to mitigate on this measurement, discovering that it doesn't work as we expected, and iterating, improving. And also this extremely frustrating when you commit it into some direction and halfway through, you realize it actually does not drive the mission you're trying to do, and you need to scratch your work, and lots of pieces of your work are wasted. So it's a trade-off of certainty, which gives you confidence and reliability, but kills excitement, and green fields a little bit of discovery process, which makes you excited, but lots of frustration. I'm personally the person that actually prefers to operate in this mode of work, look into new fields, and I'm frustrated a lot. Okay, there are lots of more questions coming. I'll try to pick up a couple of more, and I think there will be another slot. I will jump in. Does graph take into account the dynamic of a system? For example, if there are important not only features and structure of system, but also temporal pattern of activation of nodes, is it possible to solve or model such tasks with GNN? Short answer, yes. So in general, graphs are quite dynamic structures. Traffic, for example, in my work I showed you in my PhD work, it was dynamics of opinion as conflicting opinion. We see how cascades of information shared in the network is basically how nodes adopting one or another opinion, how they also flipping their opinions. It's a cascade of disease spreading. When you think about, we call these temporal graphs, and they also can be spatial temporal. It's also their topology might be changing. So length changing in time, not just the states changing in time. GNNs do work with those, and there is a special cohort of spatial temporal GNNs, which operate with similar bases. I'm not going to be touching them in today's lecture, but they also touch on the reviews I'll refer to. We can model those, but there you make some decisions on how to map those. In this lecture, I'm going to be assuming graphs are static, just for simplicity to communicate those. Next question. Markov chains were successful studying in dynamic systems. To what extent GNNs can be viewed from dynamic point of view? Okay, this is going to be hard to answer. So I'm not going to be touching dynamics of system as such. It's kind of really related to previous questions, I believe, of spatial temporal. But in some certain sense, Markov chains can also be seen as random walks on graphs. And you can see lots of random walks models, which is similar model, mentally similar model, if node to egg. It's basically when we traverse graph randomly multiple times, and this traversal becomes sequences, how we basically sequence one node to another, and we learn the sequences and the representation of each node in a sequence. How it learns node representation sequence, we already learned a lot from NLP, where we encode words in sentences, and these are very similar ideas. How actually Markov chains and special temporal part, I'm afraid I won't be able to answer in this question. Please look into spatial temporal GNNs, and maybe you'll find answer there. Can you answer all the questions at the end of the lecture? Okay, good point. Let's get to the second part, and then we'll have a break, another part, and then a break for another questions. Good. First hour. Actually goes slower than I expected, but anyways, we have plenty of materials here to go. So now, finally, GNNs. Recap of annotation in order for me to explain you the GNNs. I'm not going to be dive too deeply, but this should be well enough for us to. So graph is the same as we spoke before, is a set of nodes and their features. And basically, each node has associated feature vector. I'm trying to make in bold is a feature vector. In this case, is demonstrate a feature vector for node 1 as a 5-element some float number, which can be representation, but also it can be categorical feature, any features you would like to work. We're trying to work with more dense representation of features because then we will focus more on graph structure. And edges and their features. So in this case, I gave the most simplistic edge feature, which are edge weight. And edge features are in general a little bit less developed in the body of literature, but they also are there. And we, in our daily work right now, are trying to attack this problem. The edges also are very interesting beasts. They can be represented at discrete and finite feature domain. I'll show you one example, and we consider those as edge types. So when I showed you heterogeneous graph and showed that there's basically authorship belonging to some institution, and another authorship is basically different type of links, and they probably propagate different information, and we need to be mindful of this and model this accordingly. In these models I'm going to be describing, I'll try to assume that nodes are the same type, but this is not necessarily true. And as you can imagine, those models are extendable to lots of aspects. I'm going to be only given basics. Then we have node neighborhood. So because inherent structure of graph, we never know actually how graph will change, what's a whole graph view. And we're trying to be independent from a graph structure, from graph size. We always build all our methodologies right now that I'm going to be reviewing in a myopic local view of a single node, and is described by a neighborhood. So neighborhood of a node is basically all node it's connected to, and it's basically all edges. And we can also think about neighborhood of a certain type. So if I want to see only papers that this author has described, I look in the author and look author of edge and discover all the papers. This is also similar to knowledge graph, where we're dealing with knowledge bases and we're trying to predict. This is another very big developing applications of knowledge base link prediction for graphs, where they deal a lot of different edge types. Okay, so notion recap, and here let's dive into very simplistic learning flow examples. We have a problem representation, and this is really our design choice. This is your problem space. You need to understand basically what are these relations. Maybe they're there, maybe they just easier to be represented as features and you don't need this. Then we have initial representation for these features. Some features are inherent to the node, and they cannot be linked to anything. They will be only node features. On occasion, if we have nodes are always linked together, we can squeeze them into just one node and have them as feature descriptions. For example, okay, I'm not going to dive into examples because that'll be too much. So we have some node features and edge features. It's again, the raw data that you consumed from your problem domain. We apply GNN and we do representation learning. If I go back to typical machine learning flow, we're trying to basically do feature engineering using deep neural network approach and learn what's actually relevant given our problem structure as text, as image, in this case, a graph. And the most basic thing that GNNs do is representation learning. In this case, I'm showing representation for nodes. And let's think about tasks, unsupervised task. Unsupervised task when we don't have labels. And when GNN produces something that doesn't have labels, we're trying to create some loss which curates its behavior, how actually it should distill node representations. In this case, link prediction, and one of the best, because graphs have inherent link structure. We would like to leverage it. In many cases, it's recommendation engines. In many cases, it's basically inherent structure prediction, missing knowledge link predictions. We're trying to create a loss in a way that similar nodes should be coming together. And later, these representations are actually consumed by other tasks. Or we do direct link predictions, or we just, by training in this way, and we have also internal system done in this way, we later reuse this information. We basically have information about position of an actor in a global graph. And this is going to be very rich information which distill the graph into representation, which can be used in very simple classifiers, simple binary classifiers. And in this way, we can separate some information distillation from a graph and some specific tasks, which can iterate much quicker into two separate stages. Graph will be retrained once a week. Our online model is being basically updated in real time, most of the features. Second, semi-supervised is the most typical example, and I'm trying to focus on that one mostly. It's when we know for some nodes in the graph labels. And in this case, it's binary. We know positive label, we know negative label, and we would like to predict labels for outstanding nodes. It's similar to the previous step. We basically, starting with our initial graph and features, we iterate and update our parameters that we learned for GNN. It's basically our model that produces as output representation for nodes in this case that are predictive of a label. And predictive of a label, it's a very typical binary classification task, which probably you'll see anywhere in machine learning. I'm not going to be touching this. For example, cross-entropy loss measures this difference between predicted function, which takes node representation, and our binary label. And because GNNs are differentiable, we propagate the loss through the network and upgrade network parameters, which learns these networks. And I demonstrated it later in example. And the other one is supervised. And supervised is an interesting example I'm here providing is basically when we, again, do node representation, but also we have additional stage, and this is similar to image pooling, when we're trying to compress a graph into a single graph representation. And these are certain information we're trying to capture a property of the whole graph. And this is graph classification task. In this case, it's a great example for predicting properties of molecules in drug discovery work. So just to get here directed graphs, the problem of directed graphs in GNNs that certain nodes can be only outgoing, and they'll never learn anything from a graph, and they'll never benefit from it. And when we discussed neighborhood, I told you mostly we're going to be dealing with neighborhood of incoming nodes. And in this case, when we look in this node, how can node number 4, learn anything from a graph. And this is a problem representation. So the trick that we here are doing, we enriching with back edges, but slightly different type. And this is trick under the hood. And some models done it implicitly by a model, but equally we can think about this explicitly. So if there is a link, we're trying to also have a backlink, which gives model number 4 something to know about this neighborhood. It's a link of a different type, not to be confused with problem links, but also allows us to propagate information back. Okay, so now we're going to finally the depths of a GNN. It's an update cycle. As any neural model, it has iteration where it has input data, gets output data. Inside of it, it has some transformation parameters of which we would like to learn. So update cycle is myopic. We're going to be looking at update cycle for one single node, and this is node number 1. And I'll be using node V denominator as to dedicate to show current node. L is my iteration step or layer. I'll explain difference later. H is my hidden representation. And hidden representation is basically, in this case, my node feature vector. It's not to be confused with input feature vector, which is going to be denoted X, but in general, you initialize node with some features X, and they can be equal to this initial node representation. And many models assume that. The lastest update cycle of this output, this is going to be our representation of a node. So we have current iteration step. And this is step number 0. We haven't done anything. We have the first node on step 0, hidden representation initialized with the input features. And we have context is basically a set of neighborhoods, which potentially heterogeneous. I'm trying here to show that there might be different types of lengths. And for the neighborhood, for the context, we know representations or hidden states of our neighbors. And our goal for update cycle is to produce the final node representation after number of cycle for every node in the graph. And for this, because we cannot actually, we cannot leak data in the same update cycle, we split update cycle at which we visiting all nodes in parallel without any specific ordering. All our design procedures and functions designed in a way that ordering does not matter. So we're first trying to update all nodes on the previous state, then all nodes in the previous state, given the previous states, and so on. This update cycle I'm just describing for node number 1, it's the same for all other nodes. There are no other GNNs trained for other nodes. It's one single GNN which simultaneously apply to all nodes. It's a very important concept to understand as well. So let's understand this as context diffusion or information diffusion. In this case, we're basically trying to propagate information and through relations to node 1. So it will basically learn about its neighborhood and trying to benefit from its surrounding and understand what's around it. And this is basically called context diffusion, and its step with the current node of node V on step L, we would like to, using some update function, to get its representation for the next step. Given all this context that we have of our neighbors, and our neighbors is a neighborhood of this node, and they're feature vectors of all our neighbors on the same step, current step. So given this context, we first trying to convert them into messages. So we basically propagate each our neighbor state through a link to us. And basically it's a function which applies to our neighbor's message and results, neighbor state and results in a message. So we're basically somewhat converting it. So notice here, I'm sorry, just to step back, that there might be different types, and I'll later elaborate it. This function is function of an edge type. or it's also might be taking edge features, and the more elaborate models, we're skipping this now. Then we basically aggregate these messages into one single message. And this is very important that this function, which takes all our neighbors, has to be permutation invariant function. Typical examples are basically we summing all messages, we taking means by each dimension or element product. It's convolution, but this convolution is should not care about ordering. Most of graphs we're dealing with are in order. There are specific type of graphs where we know the order of our neighbors, but it's not a generic case. So in general case, we're dealing with functions which are unordered. Interestingly, that these permutation invariant functions that can be approximated with transformation of the message, summed up, and another transformation. And we replace these two with very small matrices or MLPs. We can actually learn this function. But in the simplest case, we can take sum of this message. And I'll be assuming the sum of this message that we're going to be taking. And the last step, we have update function. An update function which takes an input our current state and takes on input aggregated message. Okay, so this is everything to it. So let's reiterate with the formulas and how actually it looks, and all the models should be reading or looking in the papers. We have our neighborhood, our neighborhood, and all our neighbors. And this is for, oh, I realized I have a pointer, for all our neighbors. And for these neighbors, we take all their representations and apply to them some transformation function. Transformation function depends on edge. We result with a set of basically messages from our neighbors propagated through edges, acquiring information of edges. Now we basically aggregate this all together into one single message, right? And we fuse this message with our current state to produce the next state. So in this model, these two parameters are only parameters to be learned. All other parameters are basically inherent to our model. So when we be talking about like training model and learning model, we just need to learn how aggregation function works for messages, and aggregation function works for my current state versus aggregated message. In general case, this also can be learned, as I highlighted to you, but in most basic models, it's a fixed permutation invariant function. So how does it work in a larger context? So we have a node, which we're starting as our node on our step 0. And a first step, it has very limited perception field. And you would think, yeah, just looking into one hop perception field, it's actually not much different from just taking all nodes in neighborhood and converting them into features. But these nodes at the same time, all these neighbors, they also have their perception fields. And they are done independently updating for the next step their states. And so when on step number 2, the perception field widens, this node updates again perception field of nodes in its neighborhood, but because they already fused information of their neighborhood, on the second step of iteration, perception field of our node widens to 2 hop distance. And we can repeat these hops. Usually don't need to go very deep, but a couple of hops is usually enough. So it's important understanding how these whole interaction layers or iteration steps work, because quite often it's like misunderstood concepts. It's better to see that we copy graph in the layers, and each iteration step is basically a copy of our graph with different stages. So on layer 0, our nodes are initialized with our input features, or which are equivalent to the first hidden representation somehow. And then we basically update our hidden representation on layers, and the last layer contains our node representation, which actually consumed the task. And also, you can see that with each layer, this node perception field fuses more and more information of its surrounding area, and it better knows its position in space if we're doing some vision prediction, or it better knows its position against other products or users if we're doing a link prediction. So now, good to understand that we have these layers. We apply at each layer our model, and the question, is model different in each layer or not? And we basically split GNN architectures in two very different cohorts, is recurrent and convolutional. And this is why I've been using interchangeability interaction, iteration step, and layer. So when we think about recurrent GNNs, and this is maybe similar to you that you heard about LSTM, RNNs, it's where it's basically all took roots from. We iterate, and we take for each node its hidden stage, take our a recurrent unit, LSTM, GRU, update it, update it again, and we're basically using the same set of parameters for each iteration step. Since the same set of parameters are used, we basically, when we propagate error back, we are dealing with recurrent networks, and we're dealing with specific techniques for that. But also there is a very active development of convolution GNN stack layers, which instead of doing this recurrently and reusing these same parameters on every stage, it basically does convolutions, and it on every layer of the network, it uses different set of parameters. This actually results in very interesting design approaches. Our hidden vectors between different steps may not necessarily be the same. And if we're starting with this very large feature vector at the very bottom, where we really encode raw features, we can result on the very top with two-dimensional feature vector, which just does binary classification directly of our node. We learn through the diffusion process which actually features should be combined and diffused through the layers, while in this case, we basically preserve the same feature vector across. Okay, so here, just to recap, difference between convolutional and recurrent architectures. So in recurrent architectures, if you remember this function, which is basically applies to every message, every neighbor, and converts it to a message of our node, it's the same. In convolutional architectures, they're different. And so they may have different output of different dimensions, and also there are different parameters, and we learn them simultaneously. So in a way, these are iteration steps, and we iterate as recurrently we do this. But in convolutional architectures, it's much easier to see this as a layers, as an image layers, and which are duplicated. And we have these parameters to learn. Single parameter to learn here, and multiple parameters to learn in convolutional network. Now, finally, we're diving into very specific examples of basic convolutional, recurrent neural networks. So the first one, it was called also GNN, and it was back from 2009. Right now, GNN is more used as a class of algorithm, but the very first model, hence with asterisk, was proposed 2009, and iterates until converges. So it's basically the very first basic classical recurrent neural networks. And in order to guarantee its convergence, because graphs may contain loops, it enforces constraints as its loss function. We're not going to be diving into that, but the whole point that it basically takes raw feature vector, and this is X of our neighbor, of my raw feature vector of our relation between my previous hidden state, applies it. And then it sums for all neighbors. So it's slightly different than what I showed you on a generic architecture design of a GNN, but in a way we can really transform back into that representation. So back to this, we learned only this multi-ray perceptron, a small neural network of your design. The most important will be the loss function, which guarantees its convergence in the voice contribution to a concatenation of raw feature vectors. On every iteration, we basically have the same raw features of neighbor, yours, of edge between yours and neighbor, and your hidden state, previous hidden state, and then we sum them up. And this is our aggregation function. So we move since, and the first, and the first example good to show development of recurrent architectures. As more recent one is a gated graph neural networks, which based on a GRU unit. It's more standardized units, which we figured how to deal with and how to train it, which has a couple of parameters which are learned independently, but basically it learns which part of my previous state, given my input, I should maintain, which I should forget by taking combination of my input and my previous state. And so it produces also output states. So interesting change that we basically here dealing only with fixed number of iterations. We don't need to deal with convergence constraints, and we don't deal with backpropagation through time. And so there are still things you need to be mindful when you train recurrent architectures, but they are not as problematic because our layers usually are not as deep as you would train very long sequences. So what do we learn here? We basically learn the GRU unit, and this is our function of transformation. It takes our previous state and aggregation of all our neighbors. Aggregation of our neighbors, that aggregation function, as I showed you, mostly use similar sum. It's very efficient, and some feature transformation metrics for our neighbor representation of a previous step. This one can be dependent on the type of edge, and so it also can be applied to heterogeneous networks. Okay, graph convolutional architectures, and they're also called feed-forward, and they are way more understood to people because this is basically how you deal when you think about neural networks. You stock different layers, and with this deep architecture, you are trying to make another layer more and more abstract and learning more domain-specific tasks. Generally, it's inspired this application by 2D image convolution, which can be seen as actually ordered grid graphs. Why ordered? Because we always know position of adjacent pixels around, but it's actually resulted in lots of transformed worked graph. Same layered architecture as I explained to you, that we on every interaction step, we use actually different set of parameters, so we can learn slightly better approximation of a high level goal that we regress on. We have better aggregation mechanisms. So it's interesting, but similar aggregation mechanisms as an image pooling, for example, has been applied to graphs. So it's not necessarily that we just change nodes representation every step. We can aggregate nodes into meta nodes, into communities between different steps. And this is called pooling in graphs. And then we basically can create a graph representation, not directly from nodes, but from communities. And so better capture overall graph structures. We're also reusing regularization tools. You can do dropout of nodes, you can do masking of nodes, you can do similar with edges. There are lots of work on transferring attention mechanism similar to image, but here you can think about that some edges and some features of your neighbors, despite they're all kind of equal type, might be different depending on their features, on their proximity, and we can actually, using the attention mechanism, learn that. However, lots of adaptation between convolutional to deconvolutional networks and graph are needed because we don't have fixed structure, they are unordered. Neighborhood is not of a fixed size. So this is why we had to be introduced these unordered aggregation functions and how to deal with the um, normalization of neighborhoods. Again, same problems are present. We need to do end-to-end learning of all these layers. We have gradient-related problems when we go deep, but still works in practice. This is a very nice example of Leskovec from his slides, which further actually shows how similar these ideas are to graph convolutions. Our graph can be represented actually as a matrix, and it can have this represented states of all our node states. We do some aggregations, we do some dropouts, we do convolutions where squeeze make it smaller, and we result in basically some tasks as predicting node labels, new links, or generating basically the whole graph representations. So first architecture was proposed around 2009. It's a neural networks for graphs. Similar time when first recurrent architectures were proposed, so amongst pioneers, and it does independent parameters training for each layer iteration, because it's right now this each iteration of our information fusion has different parameters. We call them layers because they're very similar to 2D convolution layers. So it does learn matrix of parameter which apply to every hidden state of our neighbors, which are basically summed. And it has parameter metrics that we learn that apply. We're not learning. X is our internal feature vector representation of this node. So what it does, it actually tries to not to explicitly iterate message passing as I showed on generic GNN architecture. It takes these updates in one single loop and try to propagate in one single loop. Similarly, it can apply this to heterogeneous graphs. And when we take in basically of our edges features, which can discrete in the state and indicate on their type, we learn basically metrics applied to each edge type. In this way, we're basically converting our neighbor feature vector to a specific message according to length type. This is typical for all other methods later. So the first, like more actively used as a baseline example, is a graph convolutional architecture called graph convolutional network. As you can see, it's very recent, 2017, and most of the papers actually really advancing in the field, they are done across the last 3 years. And it's the paper that proposes a fully convolutional architecture. And now, because in previous previous architecture, we actually never dealt with the problem of having very vastly different number of neighbors. And so each node could have had slightly different results of its output, depending whether you had 1 or 500 neighbors. It's usually not a problem in that case. In this case, they normalize our neighbors' contributions. And this is normalization factor that they brought in, which is later multiplied by this is function which transform it to a message. I'm sorry, transform it to applies to me. So I'm basically aggregating all my neighbor messages by taking all their states, applying by a weight, summing them up, and multiplying my matrix on each layer, which learns how to transform their state to my state. Now applying some sigmoid transformation function to normalize it. So what is this parameter? This parameter is a normalized graph Laplacian. It's a non-parametric weight in this case. This goes into roots from other big domain of graph learning, which I'm not touching in this lecture, is spectral graph analysis. This is a very vast field which deals with graph, mostly with static graphs, studies these graphs. And I'm not going to touch it, but the whole point that we normalize contribution depending of how many edges are incoming into these edges. And so these will result in normalized contribution for region. Now, interesting one, it's a graph attention network, which was called GAT, not GAN because of clash with previous acronyms. And in this case, we're trying to learn the weight that we need to apply to each neighbor. All these functions which I give to you, they actually can be deconstructed and rewritten in the way of a generic message passing mechanism I showed you earlier. So it learns a very simple self-attention mechanism. And so it takes all our neighbors, transform them, as we already see, with a very basic function, which is we learn this matrix of weights on the current step, and applies self-attention mechanism. Then it sums up all our neighborhood aggregation and applies transformation function to derive our current new node state. The attention mechanism, I better be keeping this out of the lecture, but it's a very simple self-attention mechanism, which is looks scary, but the idea is very simple. We apply the same transformation to ourselves, transformation to our neighbor, to which we're trying to measure attention, concatenate them, and we basically have two feature vectors, vector of mine using same transformation and vector of my neighbor. And now I'm trying to learn basically using these matrix A, which transformation, which of actually those features are the most important for me to learn, which I do believe, according to my current state, self-attention, incoming state, would be the most interesting. So this matrix is basically trying to learn this, and then we normalize it with leaky ReLU and take softmax, so basically convert this into distribution. And at the end, it gives the idea how to weight contribution of this feature vector that I received as a message. And it has been shown quite a success at some cases of node classification and link prediction. Fields move on, and this model, despite it being only like going to be 3 years old, it's actually already behind, but it has all the components which are very important for us to understand anything right now. In some cases, because the self-attention mechanism is so powerful, depending on your task, it can actually drive the whole problem solution. It can find exactly the models, the neighbors, which are really relevant for you to update your state and basically have directed propagation of messages in the graph. Okay, the last one I will give in this overview is graph isomorphism network. So it's very recent, as last year, and very powerful paper. It's tried to see how powerful the graph neural networks are and trying to quantify it in more reliable way by relating to established ideas, how we compare graphs and how we basically trying to distinguish two graphs of the same structure or slightly different structure. And the idea here is the graphs that have the same structure are isomorphic, and we need to be able to say they are the same. And surprise, most of very basic GNN architectures are not capable of doing that. And this was the architecture that these very simplistic changes, and it still relies and shows basically that summation is one of the best way how we can aggregate structurally our neighborhood, but also how we should weight in our previous state with some decaying factor. It shows that it can learn graph structure and predict it. It's very promising paper from which actually right now, even our work in our team right now, we derive it. It's also a fairly simplistic model. It can be added quite a bit to add all the needs for you to heterogeneous support. Also, this model is able to overfit on small data sets, and surprisingly, some other models don't overfit. And if model does not overfit, we also question on occasion whether it's capable of learning enough. So in this case, it's great to have a model which you need to balance out on occasion. There are many more models. I'm not touching it. I'm going to refer to very recent surveys of the fields. These models are just give you the ideas how actually these components can be perturbated, and the recent work how these perturbations driven. So to recap, and this is I'm coming to end of this part, we basically have problem design choice. We have comes with design choice. We have some initial representation of features. Interestingly, if you don't have features in your problem, that can be randomly initialized. It's similar as we learn representations for text or images. We would learn their semantic meaning by extracting it from graph. Then we discussed actually which graph neural networks to models we can apply, how they actually through iterations or steps update internal representations of each node and how we result in internal representations, output representation, and basically how they can be later used as in a task. So to recap, each task also will be driving exactly how these representations are driven. And our GNN models will be learning by basically backpropagation is a loss between predicted state of this node and its current state that dedicated by a label. Okay, so now I'm taking the questions. And don't forget we have Slack channel where we can follow with much deeper discussions much later. And I will be taking a very short break after the questions and probably will need a break. After the break, we will have GNN's broader context and little very quick hands-on deep dive with animation demonstration, which probably help you to get an idea how actually it works. Very quick those things though. So questions. What do I think about ML.NET? I'm sorry, I don't have an opinion on this. I haven't came across with that. I wouldn't be able to answer. I need to take a look and maybe I'll answer in Slack later. Second question, have you considered using a graph databases, Neo4j, memgraph, Titan, Neptune, rather than SQL data storage for modeling graph as a graph? What is the pros and cons? That's a very good question. So I'll go back a little bit. I used graph databases back in past. So I started with semantic web. That was a very popular thing back in 2007, 2008, which basically motivated me going to academia. We were using semantic databases, and they were pretty much graph databases which were storing relations. You can look up all databases or DF databases. I was guilty even of writing one. They were mostly used for reasoning and retrieval. Later in my academic time, I tried to use Neo4j. It was very early. The reason being that that graph was network was offering me to run graph algorithms and specifically doing some analysis of graphs, but I actually ended up not using it because my work was very specific, and as pretty much everyone doing research, when you go really deep, you create lots of own toolings, and I end up basically having my own Python simulator, and I end up using the same code I'm using for simulator because I've been simulating large societies at scale for analysis in order not to separate those. Also, Neo4j, I wouldn't be able to ship to our computer cluster we used back in time. Nowadays, we actually don't use those explicitly, but a lot implicitly. Consider that Facebook actually is big graph database. Whole actually database of all our ants are stored in Tau. You can look up and read about, and all our objects are actually objects in this graph database. And when we query our data in our infrastructures, you query a graph node, and it has edges, links, and most of our things is basically already modeled inside of Facebook in Tau. Now, though, that graph database, like the ones you propose, they are always having a trade-off between what sort of operations they can do. Those can do very easy point retrieval and edge traversal. For things like dumping the whole subgraph, they're not optimized. And so we basically do these SQL transformations as intermediate stages to store it. So we basically dump it from one graph store in intermediate SQL, or actually not necessarily. There are other teams which operate at scale and abuse. They actually store it directly in binary optimized blob files, serialized, and they're loaded subgraphs into our training procedures. So I do believe these are very useful things, but and the last point and suggestion, right now we're basically developing for our internal framework another solution which would allow us to work with graphs in memory at actually training time. It will be one of similarity of graph backend that you will find in DGL library. They are all useful for certain operations. The trouble with each of those, they usually have a trade-off between which type of algorithm they run. Are they node-centric? Are they graph-centric? And you always need to find the right one. So I say use them. Just please find the appropriate one to your task. Never change your task to suit the database. The SQL is just a data dump. That is not really tool for us. But at the same time, it's a very universal data dump. Next question. Could you provide some resources so I can learn more about GNNs from the beginner's perspective? I will follow with those, and I will give an example of the very quick run through DGL library, and I'll link to their tutorials and surveys. So just second part of the lecture. What do you think about, okay, I'm sorry, IMLnet leaving for later. Next question, could you provide, okay, next question, how to overcome the disadvantage of distant features in graphs? They may have considerable impact even if they're small. It's very interesting question. And I will give you, so Drag, I will give you ideas. Please take a look on Graph Sage as one of very well cited GNN architectures by Leskovich from his lab. They basically sample, one of the ideas of their neighborhood sampling, they sample into neighborhood very distant nodes according to some sampling mechanism. So you can think about this as actually introducing some distant random links. And I also seen across literature other sampling mechanism where we basically enrich our neighborhood with distant links. This enrichment can be done stochastically by randomly sample some distance, or it can be actually done some curated in curated fashion, where you'll be linking because you believe those similarities should be apparent. Okay, next question. Is there a GNN to identify extraction from different data sources? For instance, can we use GNN to identify person or company by data collected from different sources, social network pages, web pages, open? Oh, I'm sorry, identity extraction from different sources. Oh, interesting. So basically, as I understood the question, is there identity extraction from different data sources? So basically, it sounds like a node prediction classification. The task that you described, it's really similar to one of the popular data sets of citation networks, very large citation networks, where we have documents described with authors, institutions, participating in certain conferences published in different venues, participating in co-authorships, and they're trying to predict belongingship and trying to predict authorships. And this task that you describe really falls into that cohort. Uh, I would believe that, especially, I'll show you the links of a set of implemented GNNs and set of papers, and papers is coded a little bit later, and they have tasks which are very similar to yours. I'll show you the receipts how to find those examples. And I do believe that if you go to papers as code and go into graphs and node classification, some of those data sets are exactly what you described. And then you'll see current state of the art, GNN models, how they perform on those data sets. This is how it starts. Then there is a code for this GNN, and you will apply to your data set. Okay, I'll give examples in second part of the lecture. They are linked in my slides. Next one, how to represent an image vector to a node. If NLP, we use word embedding techniques. And so it's basically a connection between computer vision and GNNs from what I've seen. So we sure don't want to use GNNs directly for image recognition. Convolution networks are doing that already and doing it very efficiently. What is being done here is a scene recognition of what I've seen in references. I'm not an expert in this area, so please take it as a pinch of salt. That scenery recognition tries to figure all details, and specifically trying with LiDAR images, which converts and mesh the whole space, trying to identify out of this space, which is a mesh, objects by trying to squeeze together, oh, this is the cup, and this cup finishes here, and this is 3D object, this is the person. Another bit is basically when we trying to do human actions recognition, where we building basically skeletons by identifying joints, and joints are examples. But most of the work is basically where you're dealing with mesh and when you're dealing with objects, and how you model the mesh, how you model relations between objects are converted into GNNs. Next question, what is the best approach for a beginner to decide which GNN architecture is the best for a specific task? I'll give examples in the second part. Simple receipt I have is look into benchmarks, look into paper with code, look into implement it into the libraries. The most important is to find a proxy open data set which is similar to yours, and follow leads on that. How applicable are GNN for sparse data or tasks for which you have very little data? Actually, GNNs work better for sparse graphs. Surely we cannot deal with fully disconnected graphs, because then we don't have any information to propagate. But when you have very dense graph, GNN suffers from basically very large neighborhoods. And there are techniques on scaling, which I will explain you. Excuse me, but sparse is actually even better on occasion. A general question about GNNs. Why do we need to overfit data sets? I thought we prefer to omit overfitting in training machine learning. So does it work differently for graphs? Now, you're right. Your intuition is very correct. We don't want to overfit, and we want to stop before overfitting. But on occasion, we want to push model to extreme, and this is basically trying to understand how much model can learn. And the question here, can we add, by adding more parameters to model, by building bigger model, harder model, where actually is that edge where a model basically learns whole domain completely and overfits on it? This is more of a question when you're trying to push models to a limit, and overfitting is actually pushing model over edge. And seeing where it's overfit, you basically know where is the best moment that it generalizes before go overfitting. If you remember from general machine learning courses, you're going to basically look into your training loss, and you're going to be looking into your validation loss, and validation loss goes up, training loss still goes down. So on occasion, when you have very complex domains and complex models, you actually never see validation loss going up. And it's kind of disturbing. Still, modal works well, but you cannot push modal over edge. So it's just for us interesting to see modal boundaries. Yeah, please don't overfit models in production practice. Please, can you talk in general about the machine learning and econometric model for forecasting energy finance data? So while I've been working in Southampton, a big part of our lab been working on electric grids. And we were studying specifically how energy distribution works, and they were modeled as grids, specifically to move into decentralized energy generation and distributions. I'm not an expert in this area, but they were been working a lot in optimization of these networks and graphs, especially energy pricing and distribution. If you'll be interested in this domain, please look into decentralized energy networks and optimizations in them. I won't be able to dive much deeper in that. I'm years behind from this energy domain, even like side exposure. Can you maybe elaborate a bit more on which approach there are for node prediction in knowledge graphs? Do you know any applications? So I've saw applications, and knowledge graphs are one of the core examples of link predictions, of properties predictions, especially links predictions. And I followed a couple of lectures. I've seen those data sets are around. I haven't touched those because I just never worked with knowledge graphs since semantic web, which doesn't exist anymore. So please follow again on links that on the data sets I'll show. And in review papers, survey papers, I point, they actually mention knowledge graphs. Probably you'll find good reference points for started there as well. GNNs are prone to propagating bias as other ML techniques. Are those approaches other approaches to reduce bias? Yes. Yes. So basically, all ML techniques pretty much are prone to propagate bias. And one of the basically pitch for graph networks and study them that we actually learn on existing relational bias. And this is basically gives us more information about task. And when you hear the word bias, it might be different meaning, but it implies that if bias exists in the data set, it will exist in what we learn. So for that, we have separate efforts, and these separate efforts about regularization, separate efforts about trying to understand how also the whole ethical part of our prediction models. In FAIR, also Facebook AI research, they are having a separate work stream which later evaluates our models and also helps us to guide how to create better examples, how to prevent us creating things which can be easily picked up and mitigated. A lot of this work, though, has to be done on label generation, on some data transformation, on regularization. It's not a thing that we yet know how to embed directly into a model, and this is still kind of expert area. In a very simplistic manner, very simplistic, please follow more on FAIR publications and posts by Facebook. We're trying to take this as a controller agency, and we're adding specific ways how we control models for biases and other models which control existing models. Okay, sound level is quite low. Make it louder. I'll try to do it during the break. Does enriching a node link it to an unrelated node sometimes? It may learn unnecessary information from otherwise unrelated node. So this is link enriching. This is a technique which comes with regularization, and it can be mixed also with attention, which will figure whether it's relevant or not. In general, you really want to have also very distant links to push graphs away. If you want to have negative links in a link prediction task, you basically deliberately create negative links. So yes, there are drawbacks, and there is no golden answer. Whether it works or not, you basically study on your data set and on your measurements. And this evaluation part is right now the biggest concern in research, and I'll show you a little bit later. We create better benchmarks and better evaluations to understand how these old techniques are beneficial or not for different tasks. Do message and update functions help parameters to learn? So I try to highlight in red only those parameters that are learned. We basically learn parameters that transform states of other nodes according transform state features of edges and your previous state. But since we're doing representation learning and we update them, we basically learn in the model those transformation parameters, but given initial state, even random state, we can actually learn age and node representation and graph representation. Could you please comment on permutation and variant convolutions you mentioned briefly? This is permutation and variance is a core difference between convolutional networks and graph neural networks, because when you look in a graph network, you basically rely on structures. You know the order of the pixel, how they're related to each other. In the case with the graph, we don't know their order. The order is arbitrary, how they are written to our database. And permutation and variance here implies that we need to be consuming information from our neighbors regardless of their order. So all together, and we're trying to basically use functions which do not depend on order. And permutation and variance here, if I'll fuse messages clockwise from these neighbors or anti-clockwise, I will always result with the same number or same vector. So this is basically permutation and variance. And all examples I used before were simple models. They were just summing them. And sum was permutation and variance. The result of a sum doesn't change if you replace summation. But I also very briefly mentioned, and there will be more in that in surveys, that we can learn functions which are more complex than sum, which are doing this transformation, especially when you're dealing with very nonlinear spaces, which also result in complex transformation, but they are permutation invariant. And that requires you to learn two parameters, one for each message, which is summed, and another for overall sum, another transformation function. Good. Can we draw graph and link between two different programming languages exactly on the running time of the code? Yes. So basically, GNNs are applied to code. It's one of the applications. Microsoft Research really pioneering this direction of work. They are using converting code into a graph, and anyone familiar with code compilers would know this is done internally, and trying to predict whether a developer has made a mistake, used wrong variable, whether it's a hidden bug. They learn on examples, and with GNNs trying to basically discover these aspects. I don't have references, but you probably can find Microsoft Research GNN. They're using gated graph neural networks for this mostly. Please look up online. What's the difference between spatial GCN and GCN? I'm not sure I no exact answer to this question, we can follow on that one in Slack. Okay, thank you, everyone. I'm actually gonna be timing myself to give a rest to everyone, and let's see each other in 5 minutes.
Oleksandr, Oleksandr, do you hear me?
Hello. Okay, I'm back. Give me please a minute, second to check my. I would like to do something with sound. If it's quiet for some people, sorry about that.
Oleksandr, do you hear me?
Yes, I hear you.
Now we should have 30-minute break, not 5.
Oh,
Yeah,
okay.
till 13:30.
So we restarting. When do we restart?
Uh, we should start half to 2 p.m.
At 2 p.m.
No, 1:30.
Yeah, okay. I'm sorry. 1:30 is the next lecture or
So
11?
we have 20-minute more break.
Awesome. Awesome.
Mm-hmm.
Thank you. I didn't know about that. Sorry, everyone, if I misled someone. Okay, so I'm setting timer and I'll be back in 22 minutes. Thank you.
Okay, thank you.
Welcome back, everyone. Still 1 minute, and we restart the second part. Okay, second part is go. Good. So welcome back. We discussed graphs. We discussed um, core GNN architecture, how it's actually built around local visibility of each node and the same mechanism applied to every node, how it's basically propagated in time or layers. And now let's try to understand where it's being actually used and what is that with application. This is going to be more applied part of the lecture, and there will be very quick hands-on just to demonstrate mostly relying on visualizations. And I'll provide mostly references and links where to go from here. Good. So the graph neural networks is actually not the only approach for learning on graphs. And we need not to be forgetful about others. And here's one of the ways how we can structure them. And as you can see, that there are lots of other deep graph networks and approaches to learning graphs in deep fashion. And deep neural graph networks, that's what we've been discussing here. It's only a subpart of this approach. We looked quickly about recurrent, mostly focused about on feed-forward networks. Feed-forwards have also okay. Okay, sorry. Just quick announcement on the Slack. Okay, so back to our discussion. So GNN that we discussed is only one part of deep approaches to learning graphs. And we need not to be forgetful there are others which are not neural-based, and these are examples of deep Bayesian graph networks. And they're rightful place to be and very interesting mechanisms. They also, we need to slightly separate deep generative graph networks. These are specifically created for creating new nodes, graphs, and basically generating similarly as we generate images and text. Their architecture is very much similar, but because task is so different, there are also more dedicated problems to this domain. What's not explicitly mentioned on this diagram is also that we can actually split our approaches into spectral and spatial. Spatial approach, and it's more in feed-forward graph neural network is just when each neighborhood, each node looks in its neighborhood, and we go from there. And it's more like a message passing paradigm, which I explained earlier. Spectral is based on more on graph theory, and this is long-lasting field in mathematics, which are more focused on analyzing flows in graphs, graphs as matrices, static properties, is trying to decompose it into eigenvalues and understand contribution of each node. Those methods are very important for us to create theoretical basis for our work, and they will continue excelling. But because they build on all these mathematical toolkits, which are more dedicated for graphs that are static, undirected, more homogeneous, we kind of miss omitting them in this part, but probably they will be a big part of research looking forward. So It's important to also remind about generic part of machine learning, difference between inductive and transductive learning, which is more prominent in graph learning. So if to simplify, inductive learning has two stages, and this is typical machine learning that we all learn in our courses. It's basically we have training where we have training data with labels, and if we don't have labels, we basically don't know what to do with this piece of data, and our classifier, be it logistic regression, does not know what to do with it. So we train this classifier, and then we apply to new unknown data, maybe which wasn't even present during training, and predict on it. So this is typical machine learning flow that you know inductive, but there is also transductive flow. And transductive flow is basically when you have all data on which you need to be doing some predictions during your training time. And you basically can train and infuse new data in order to do new predictions. In this way, we basically can uncover probably some structures in unknown data that we would like to classify, and we won't be relying only on what's probably limitedly accessible in our label data set, which quite often might be not fully representative. But it's crucially on graphs and how it differs that if we look on transductives, basically want to predict for a couple of these nodes and labels, we have all the graph and all the structure at training and prediction time. And graph is the same. And so we basically can apply mechanisms which don't need to think what will happen if graph will change at all. And inductive learning, which pretty much most of models already offer, not everyone, it considers what will happen if we'll add a new node. Can we quickly predict links for this node, recreate representation of this node for any other task? So this is a minute difference that you could need to know when you will be choosing graph algorithm suitable for a problem. Think of the problem inductive or transductive. Transductive problem, your graph is fixed and you basically want to know something more about its nodes, you want to find links in it, you basically don't expect to add new members. And inductive, where you would be changing your graph and you basically would like to do predictions for different graphs that you haven't seen, for graphs with new nodes, for changing topology. Another aspect when we're basically going hands-on on again, how to scale them. Let's be honest, it's not a problem. Don't deal with this problem until you get to it. So in most of the cases, if your data set fits in memory and fits in a GPU, if you're doing training with something like PyTorch, it's fine. It's totally fine. Don't look into improvements until they're necessary. Should you start struggling, and for example, you need to distribute your data, you need to think about how to scale the methodologies, here's like what research considering. First of all, sampling. Unfortunately, all solutions come at the price of corrupting graph completeness, and sampling is one of the first ones to give an example. So here we have neighborhood of the node V, and you see that what we can do, we basically can consider only subset of our neighbors in our state update. Which neighbors to consider? It can be randomly, or it can be designed with some predefined fashion in which we learned which neighbors are more important. There are different models of doing these things. They're also sampling in a way that we separate graph and sample basically graph into subgraphs. It's partitioning when we basically trying to cut it with like scissors into parts which are mostly coherent and internally connected, or clustering, which is more like community detections. We're trying to discover inside of graph very large structures and trying to preserve those inside of which part. Bigger difference in partitioning, trying to cut is like similar pieces, clustering, community detection more into inherent structures which are defined by graph properties, which we mentioned in the beginning. Another way we basically can, because we're dealing with convolutions, as I mentioned before, we can have layers which actually simplify graph. And this is an example where we, given this graph structure, learn that some of those nodes are, given their initial feature set, inherently very similar and connected, and they can be abstracted into meta nodes and basically do aggregation of a graph and simplify graph. This is quite often used when, especially we want to do graph embedding and trying to reason about graph representation at all. And there are always modal trade-offs. Modals I mentioned are not the only one. There is a whole new developing very actively, but all of them have different cost in time and memory, depending how many actually parameters you need to sift through when they are doing predictions. Depending how many they need to store in memory in order to do traversals. For example, recurrent neural networks, we need to have copies of every step in order to do propagation, most of them, not all. For example, models which based on spectral analysis of graph and decompose it into Laplacian eigenvector matrices and doing all that work needs to do the spectral analysis of graph, which can be n cube in size of the matrix. Still, there are algorithms which all exist to simplify those, approximate those. We need to be mindful. Some parameters are model parameters, and some are just basically motor improvements where we sacrifice precision for speed. Applications. We spoke about applications a bit more at the beginning, so just to remind here, they are applied. They don't have their own domain GNNs. They apply to all existing domains where we can infer links and relations between objects in space, like in computer vision, like point clouds of LiDAR, trying to figure whether an object ends and starts another one, where action, human action identification. Again, natural language processing, which we discussed as either second level task where we deal with pieces of documents and relying on relations, how they relate to each other, or trying to do sequence generation because sentences are better represented in graphs and maybe it's better to model them in graphs instead of just a sheer sequence. There are experiments like this. Traffic we mentioned, chemistry and drug discovery. And one of the examples I've been looking at is these data sets are available and many people right now using them as well for their baselines, is trying to predict whether certain molecules will have side effects or not. And this is basically graph classification because each molecule is converted into graph where atoms are nodes and bonds between them are different links. And source code analysis, we also mentioned earlier, Microsoft Research and others are doing by converting source code in programming language into a graph and trying to find problems with it and suggest it before it's actually going to happen. Okay. So now a bit more, and we also touched a bit more than expected for the first part, that GNNs could be a special CNNs, excuse me, convolutional neural networks can be a special case of GNNs. First of all, it's where inspiration came from convolutions on images like lattices to degrees lattices to graphs, but equally, it actually can be traversed back. So the idea here, if we kind of have a lattice, it's not necessarily can be an image. It can be some other domain representation where we, for example, sample some spatial environment altogether. Information that will be presented in each individual node might be a bit more than just a value color. It's actually not a problem, but edges might be representing a bit more value, which won't be captured by CNNs. So edge values will be better captured by GNNs. So consider this. It's a special case. It doesn't mean that GNNs should be applied to CNNs probably, but if there are tasks that right now only apply to CNNs, if they have some extra information that GNNs can benefit, we can use it. There is another area of study right now. It's a DeepSat, a recent paper at Insight. Sorry, it's when we're trying to understand and classify a set of objects. a set of faces altogether, a set of documents altogether, and we're trying to find commonalities between those and trying to make some prediction regardless to how many elements we have in this set. Previously, other models usually rely on very strict number of things. So the question here, can it be the deep set is more, has some more relation to just belongingship? Like, for example, age of each element, it can be encoded. And can we have some relations between them? Because a set essentially is a fully connected graph, which is a complete graph. And if we have some extra information, just slightly extra, we can move from sets modeling to graph modeling. We already attempted to do so in our multimodal classifiers, still work in progress, interesting direction. So now that speeds through, I actually turn a bit more practical bit. And first thing, how basically what should you do to start with GNNs? This is the next 20 minutes, 30 minutes before we will go back to questions. So now get GNNs hands-on. And what are you gonna do following this lecture? So you probably would like to learn more. And a good place to start, surveys. And there are very recent surveys. It's a very active field. And I would really advise to look on the most updated ones. The first one is a gentle introduction to deep learning graphs. It's actually the second version. Previous one is a half a year older and it's already improved. Please look in detail in this one. It's very accessibly written and have very good comparisons to get you a structure and point to application tasks. It actually covers much more than I did in this lecture because I was trying to focus on a very basic case only. Then we have another surveys, and this is a good example that I would recommend. And the last one is a very interesting one. So as you notice, the field is extremely dynamic and young. Lots of development happened over the last 3-4 years. And that means actually that data sets and methodologies how we evaluate, they're not comparable exactly between graphs. There are potentially cases where simpler models can outperform more complex ones, which are published right now, should they be compared in very similar settings. And actually this drives a very good standards, how we should improve our calibration to understand which GNN is the best, and especially in which setting is the best, and having better comparison apple to apple. I would recommend this paper for a comparison of graph neural networks, which is specifically for one problem, but it gives you an idea how actually we deal with networks and what are the problems that exist currently in their comparisons, why you could not been able to drive conclusions when you have read the original paper, and what we learned since. So now really hands-on, and I highly recommend papers with code. I've been looking in there before, but recently, as last year, they part of Facebook, and I believe I saw folks even in London office before they all went to work at home. And papers with code is one of those more popular ones. There are others, but this is where I've been looking at. They have dedicated sets to graph problems. And if you open this area, you'll find there are lots of sub areas, and they have a few which are exactly relevant to what we're discussing today: representation learning, rank prediction, graph embedding, node classification, graph classification, and more on. For each of those, like here, I'm showing you node classification page, you will see, and there will be a list of data sets. You will look into these data sets, and some of those data sets are likely to be very relevant to your problem space. You will look through this list of the data set and find one which is most closest one. For example, knowledge-based discovery, transport network optimization, or link prediction, recommendation engine. Notice that data set really implies data structure. Task which we do might be different. We can predict and do recommendation in the same data set. So look at data set which mostly represents your problem space, and look on task into two sides. When you find two, for example, I wanted node classification and I did site here data set. I can see on one of the metrics, basic metrics, progression, and how the models perform against each other. Now, let's take this result with a pinch of salt. It's very indicative, very important result. It's not exactly the most comparable because often they have slight variations, tiny variations in their setup. So, for example, these two experiments conclude that this one is strictly better. I probably requires a little bit more research. But for your starting point, that really is enough. It's enough for look what is there, especially when you click on each paper, you'll find implementation of code for this paper. And you can actually dive much deeper trying to understand or actually simply hack it. Take this implementation and apply to your data set. So the nice bet that if implementation is tested and it performs well for open data set, that means it's bug prone, it's clean, which is the most important bet when you do any machine learning work in this area. So implementing a GNN, next step. So you want to learn these things and you want to apply things in reality. You can do your own code. You can do NumPy, you can do MATLAB, Octa, we mentioned. This is a very good way to learn minute implementation details. Nothing wrong with that. Lots of these algorithms, they are really down to some matrix computation, and you really can code up in any language, in any environment you would like to. Now, the trick comes only when you basically want to scale it up. And this is where the existing frameworks helps you. So when you're using PyTorch or similar libraries, they already give you really big baseline for scaling, for evaluation, for creating training loops, for doing gradient propagations. All of these done for you, and this is important. And most of our work we're basically internally doing on PyTorch right now internally. There are others, TensorFlow, MXNet, you name it. Also, there are already dedicated GNN libraries. PyTorch Geometric is one of the earliest one, and it applies one of the paradigms, not exactly all networks implemented there, but this is like more lasting one. And the more recent one, which has actively been developing really through the last 2 years, and I'm looking through it following more than half a year, and I'm impressed already half a year development, is Deep Graph Library. We're gonna look into DGL in a bit. And here is a comparison. They really already trying to beat their benchmarks, and they're showing they at least as fast or better. And this is where actually using the library comes in really handy when you do performance optimization, when you do distribution. But frankly, from my perspective, it's also bug-free when you're using building blocks, each of which is basically being really nicely tested out. They also show that in some cases, because they're much better optimizing memory and training abstractions, they're much faster. So yeah, I haven't actually mentioned the last bit. Yes, so it's inevitable that everyone probably will end up in their solution because you need to have tailored to your problem space, tailored to your infra. You're in academia and you're likely to diverge into a very dedicated solution. So you probably go much down to starting your own solution, or you in industry and you'll go into other direction, everything that touches much closer to your infrastructure. Internally at Facebook, we're building our own graph neural network library. We're hopeful that it will be released one day. Right now, it's still very young, and we're basically experimenting with it and rebuilding it as we learn how it's actually better to be done for our tasks, and it's very tailored to how to scale. We're really focused right now on these aspects. And yeah, I'm proud to be in this team to build it and contribute to those bits. So another aspect, if that will be implementing, as I mentioned in the review of paper as code, is exploring through data sets which are there. And there are data sets which are really, really close to your tasks, most likely. Find a data set that reflects your domain and follow on this leads to find papers which are doing tasks for this data set. So you implementing GNN, confirm always it also performs as expected on open data set. Be it your own implementation, you did a custom implementation when you tuned your model, even inside of DGL or our own framework, always try to see whether they haven't broad benchmark. If you are not doing that, you are not testing yourself, and you probably may not even implement efficient solution. By the way, if you'll get good results, always publish them, share them in any way. So rouse the data set. So we all end up with custom data set. It's actually much easier than you think. The same data sets we already have. We treat some of the features which are relations and we discard them right now, and we transform them into features as relations. And then we make a decision how to split edge types, edge features, node types, node features. This is basically a design decision, but usually it's already there in the data set. Trickier it comes when you're trying to split the data set on a graph into testing and training. This is where things more often go wrong when in our classical machine learning, where it's much easier to do these K foldings because you need to think more careful. How do you want to design your test and validation? Do you want to remove some links from the graph? Do you want to remove some nodes from a graph? Do you want to remove some labels but keep the graph? Do you want basically to chunk off some subgraph and have withhold them? And these things tend to require for each task a little bit specific implementation. So this is very careful. And this actually led to new initiative called Open Graph Benchmark. And here is linked as a couple of research labs which are operating in this, trying to combine all open data sets and hide them behind easy downloaders. By the way, those downloaders are embedded into libraries like DGL, not specifically this one, but downloaders of open data sets. But this one also provides you set of data sets, set of data loaders, evaluators, which also care about nice and proper training and validation splitting. So you'll be really doing what you meant to. And finally, you can actually compare your results directly against leaderboards and see whether these changes that you're trying to experiment. And usually, as I showed you, there are lots of building blocks, and you'll be trying to experiment instead of model with those building blocks. How are they actually improving this domain? So please use those tools that will allow you to kickstart very quickly. And you start with your open data set, and you just at some stage replace this data set with yours. Okay. Okay, so now I'll have a DGL demo. And this DGL demo is a very quick one. Just to give you pointers where to start. I decided to take a DGL demo from its tutorial. When I looked through they're actually doing quite frequently right now. Their presentations and hands-on tutorials, and I would give a recommendation follow-up. They just gave in April 22, 2020 on the DAP conference a very long tutorial with deep dives, all the lectures available and materials all available online. I'll give you just a preview just to give a taste. What is that and how to visualize this bit so you would reason about it easier. So DGL uses a couple of different backends, and one I'm using here, PyTorch. I can use TensorFlow, MX. It does not matter in this stage, but usually when you're using one of the backend deep neural network libraries, you're reusing its concepts in order to simplify your life in metrics and computation. So here we rely on PyTorch. So let's start with a problem, and the problem is around very typical graph. I don't remember, it's actually in any graph book that you'd see it, called the Harry Karate Club. Been used in studying graphs a while, and it basically people belonging to Karate Club who are related to each other and how they basically communicate outside of club with each other. And they're centered around two main nodes. The director of the club and lead instructor of the club. club president and the lead instructor. And you see they are basically focal points of two subgraphs, and the tasks which usually we do on those graphs are community detection. Can we split and figure who is actually belonging to which community? You see there are actually that belonging directly to both or belonging directly to both communities. So the task we're going to do today will, given just a graph, just its relations, we'll try and two labels for one node, president, another one, the lead instructor, trying to predict the labels for all other nodes in this graph. It's a semi-supervised problem where we will be doing a node representation. So this here is a graph. Graph is basically encoded simply as a list of sources and destinations, meaning node 1 connected to node 0, node 2 connected to node 0 as well. And this is all our edges, as you remember, from matrix. But we, because we model in DGL them bidirectional, we just copy them by reversing. So we take one set of edges, change head and tails, and add again. So we'll have basically unidirectional graph with each edge as two directional edges back and forth. So I'll try to running it. So we can look into our graph. We see that it has 34 nodes and 156 edges. And then we're using NetworkX library. This library is well established. It's a very Pythonic library, which allows you to analyze graph and provide lots of measurement and quantities in graph, and also visualizes. And this is a very simple way to visualize it. It tries to stretch nodes according to its relative positions to do its 2D visualization. And well, here it is. And probably I shouldn't have run it. Okay. So now let's dive into how we work exactly with our graph building. We're using Torch in PyTorch. We're going to be using its parts and we're going to be using its functions. And we generate basically tensor of for 34 nodes. We generate a vector of 5 elements. It's randomly generated. And as you can imagine, this is basically, we have a matrix for which we have number of rows is number of nodes, and each one is represented as 5-element vector. When we look into this vector and we're basically putting into graph, we squeezing, this is basically we create the graph and we build it as a DGL graph. It's presented in memory inside of DGL abstractions, which also allows us to do better traversal on it. If you could think about this, it's kind of in-memory graph database. So we assign to node data features, and we basically associate this. And it does associate one-to-one all of these node representations. Now, if we look into one node, features of this node and node number 2, we will see basically some feature vector, right? And this is what is randomly initialized with. Well, we can take a look on 2, and you can see it's basically the same, just all node has different vector features. Our task will be to learn the one which will be the most predictive for structure. So we're going back to GCN, and I explained you GCN. Here we basically have much simplified GCN. It even does not do any weighting. It computes a representation of its node by basically summing up representations of its neighbors and applying small function. So in this specific example, DGL allows you to implement models in a couple of different ways, one of which is explicitly creating this message passing paradigm and modeling message passing, and it does under the hood optimization of those bits, or also allows you to use building blocks that it provides. In this case, we're just using the building block. It's a convolutional layer, very generic, that implements this bit. Now, you remember we were discussing these layers or iteration. or steps where we update our graph. Here we basically unroll them. And when we're creating our recent model, we create two layers. Which one will be first number of input features per node and size of its hidden representation. And second one will have hidden size representation and number of classes. So this is basically our input size, input features as we generated. It's going to be 5 per each node, and probably number of classes we're going to need to distinguish between two classes, where it's in structure or where it's a president. And we defined a forward, it's a feed-forward network, very simple convolution as we define in convolution layers, and it's basically take our graph and its inputs, and on the first layer compute a hidden representation, apply activation function, compute second representation. These two layers will have different parameters to learn. They're hidden inside of their definitions, and they'll have different hidden representations while being computed. And now we defined it, and it's basically input feature vectors size of 5, which we had hidden is basically in between these two layers. This first layer will have input 5 and output 5, and it's also 5 will be considered in second layer. And output after second layer will try to predict each node representation only out of 2 elements. It's going to be a vector of 2 elements, and we'll positionally encode it. If it's position number 0, it's one class. If it's position number 1 is more active, it's another class. So we prepare the data, and data preparation is extremely simple. We take all inputs as our existing embeddings, which are generated randomly. We give, for 2 nodes, we give labels for instructor and president, and we just do binary classes, 2 binary classes for our loss computation. And finally, we basically do training. Training, it's typical for neural networks. We're using gradient descent, and we're using Atom Optimizer for this. And I am ignoring these parts, which basically I used in order to visualize. Our nets is producing an output. It basically runs with its parameter as it's randomly initialized. It's for each convolution layer randomly initialized matrices, as you remember. And we store these intermediate results. We compute output, and we use softmax in order to figure which class, because it's 2-layer output at the end. For each node, we have a representation, a vector of 2 elements. And we compute loss. Notice we compute loss only for these 2 nodes. So we actually don't compute loss for all other nodes. We still do update them because we don't know their exact relation. Probably they might have went into a neighborhood of these nodes as well. So in this way, we basically propagated 1-2 hops away from our labeled nodes. So because we have 2 layers. Now we have typical for PyTorch models, we have computation of gradient, we have backpropagation, which updates inside of our model those matrices on each layer independently, and it just computes it. This is super fast. I'm scared to run because you notice it didn't run. Yeah, it runs. And I had actually the model pre-trained. I'm afraid I'm broke visualizations right now because of this, but it's okay. Let's continue. So now visualizing this bit, and this is a bit where this visualization really helps you to understand. Always try to look into the graph, and there are a few tools that will allow you to visualize. In this case, we're basically trying to see how each node last representation, this is 2-dimensional vector on last stage, relevant to each other, how basically they are close or far from each other. And here is a starting point where we started on epoch number 0 and how our graph evolved over time. This is different training epochs. After each we changed our network parameters, and it has been recomputing every time new node representations in the final layer. And we can see that actually observes these nodes 0 and 33, which is the only two labeled nodes, and they basically stretching our representation, trying to be more away from each other, pulling their subgraphs with them. So if just to repeat this bit, it's 33 and 0, they're pulling away. And if we started with pretty much random labels, already after a couple of epochs, we start seeing separation of labels for unlabeled nodes. So basically, these are predictions, and they seem to be coming correct. So now this visualization is more like a showing you strengths, how these two representations separated these classes in graph. But let's look how actually it looks in the graph representation statically. I did this one because it's more interesting to and straightforward. Node 0 and node 33 are the only labeled, and we're trying to predict those labels. And first epoch, we are basically random. Epoch number 2, we learned how to predict this node. Well, something else fires, because we basically learning parameters of the models which are applied for every node, so probably can apply somewhere else. And you see it's slowly recoloring the graph. So it's slowly learning how to aggregate its vicinity. Now, this run was not successful, and it did not recover and recolor all of these nodes. This is stochastic, and when I've been running this notebook multiple times, so you receive multiple different results. Also, frankly, two labels is a little bit overstretched to expect to learn model. There are cutting edge research how actually to do this by pre-training on tasks and other tasks and learning on related tasks. You can look into few shot learning approaches, but in this case, it's rather everything for demonstration. I'm afraid my charts are not coming. Okay. Okay, they're here. So let's take a look how second run has changed. It's different dynamics of stretching. I actually don't see node 0. Okay, node 0 is bottom, node 33 is here. You see that some nodes even pulling farther away from node 0. Let's take a look how they color the graph statically aligned. You see there was fight between them, and so later epochs it was recolored and added. Okay, so this was a quick demo, and I'm not going to do deep dive and tutorial on DGL. We are lucky that DGL team just recently in April did a very deep dive and tutorial that they have released from the web conference. You can see it online. You can find their materials. If you'll find that a little bit too much, always go and look into their docs and tutorials. They are very accessible and very basic. They allow you basically to reuse existing models without diving into, or they allow you to really build models from message passing or matrix abstraction from scratch. Everything is there. The nice bit that actually they also have lots of models implemented there. And if you look into model that you'll be interested in with DGL, which I do quite often, I always find something to look at. So the last bit, and this is going to be, for me, second part of the lecture a bit shorter, is the questions and follow-ups. So please now ask your questions on Slido. Most of the questions that we run in the first part of the lectures. You always can follow later questions with Slack. I'll try to support those through the week. And always feel free to reach out and leave feedback about this lecture, ask more about it, ask about Facebook AI research, or any send feedback or corrections to whatever I made mistakes and help and do erratas. My emails, and I see you in Slack. Somewhere online. And is there any questions on Slido right now? I'm going to be taking them. So the first question that is there from the previous part of the lecture, which I had time to look into, what do I think about ML.NET? I will be frank, I actually never used it, and this is machine learning framework developed by Microsoft for .NET, and I just happen to be that there are a few of those, and I never used .NET technologies. So I cannot really comment. I know there are lots of good solutions around, and I'm not gonna telling you that one is better. The one that actually works is better. So if it does the job, do it. For me, the most important is to find things, and why I'm actually offering people to use libraries which already build some basic blocks, so you would spend more time on exciting bits than frustrating bits. So find things which did the baseline work from you. This is the only comment I have, but sorry, nothing specific about ML.NET. I share the demo notebook. It's linked. It's actually a little modification of DGL default demo notebook. I'll share those in Slack channel, and I'll also share the slides, so you will follow on the links. Okay, and the same questions after that. Good. Thank you very much. If there will be some more questions coming, please leave those questions in Slack channel. I will be supporting those through the week, or here is my contact details. Feel free to reach out. Thank you very much for those who stayed for the second part as well, and for today, and hope to see you somewhere else discussing graph neural networks. Okay. I will be disconnecting. Thank you.